Bismillahirrahmanirrahim. And dear students, we'll start lecture number 2 of week number 11, and this is about the initial few concepts of continuous random variables. As we know, we have random phenomena that can be described through discrete random variables. Similarly, we have many natural life phenomena which can be handled through continuous random variables. For example, temperature in a room is a continuous phenomena. For example, arrival time of a particle is a continuous phenomena, and so on. Voltage across the resistor in a particular circuit is also a continuous phenomena. It can be taken as some random variable. So today's lecture will be the basics of continuous random variables, and we will first describe the bridge between discrete and continuous random variables. We have already learned the necessary concepts of discrete random variables. Now we'll initially make a bridge, and there are just 3-4 points that must be kept in mind so that you can easily jump conceptually from discrete random variables to continuous random variables, and those 3-4 points are as follows. First one, always remember that the probability of a particular point of a continuous random variable is always equal to 0. This appears strange, but I'll show you later how it can be understood. The probability in a continuous distribution, the probability of a particular point in that distribution is always equal to 0. If you recall, in the cases of discrete random variables, p sub x, where x is a discrete random variable, if there is some occurrence of this random variable for a particular value of x, so for example 2, if we write p sub x of 2 and that x was part of the distribution, that was part of the set of assumable values of x, then it had some non-zero probability. But if we say the same, not the same, some continuous random variable x, and we say that now what is p sub x of 2 if x is a continuous random variable, and what is the probability that this continuous random variable assumes a value exactly 2, then if x is continuous, this probability will be 0. So that is why I wrote here that the probability of a particular point in a continuous distribution is 0. How we describe continuous distribution, I'll show you at some stage in this course. So this is the first important point to be kept in mind. The second one is that in the discrete random variables we use to describe phenomena, for example, of expectation and variance through summation, but now these will turn to integrals because we are handling continuous phenomena, and you know summation is also a kind of integration, but in discrete terms. The third important point is that the probability distribution of a discrete random variable, we used to write it as PMF, probability mass function, but now when we take continuous random variables, these probability distributions will be described through this concept of probability density function. So we will think of probability in terms of density. So density is always a continuous phenomena. And the last one is CDF. Terminology of CDF for discrete random variables will stay the same, except that now the plot of CDF will be a continuous plot and not a staircase plot. So if this is understood, I'll move back to this point number 1 and give you a conceptual note with example on how to easily imagine why the probability of a random variable x, if x is a continuous one, then the probability of a particular point in that continuous random variable is 0. Why it is 0? Let me now show you. So take an example of a professor arriving in a class. So the example is a professor always arrives in a class between, say, 9 to 9:10. So this is a 10-minute interval. So if you know that the professor always arrives within this interval, you will say that the probability of arrival of this professor is simply 1, because you're already given that the professor always arrives within this interval. But if I reduce the interval, say from 9:00 till 9:05, which means now the initial half of the total 10-minute interval. So now what is the probability that the professor arrives in this interval? Obviously, you will write it as 1/2. If I further reduce, say from 9:00 to 9:02 and 30 seconds, which means further half. So 1/4 of this total 10-minute interval is this now, just 2 minutes and 30 seconds. So if I ask you what is the probability that the professor arrives within this interval, is 1/4. And similarly, if I reduce the interval, say from 9 to 9:01, just 1 minute interval, so you see out of this total 10-minute interval, we are just picking the first minute. So the probability has to be 1/10 of the professor arriving in the class in this interval. So if we keep on reducing the interval ultimately till, say, 9:00 till 9:00, then what is the probability that the professor arrives within this particular interval? It has to be 0, because you see a decreasing trend in the probabilities when you reduce the interval. So when you take an interval from 9:00 to 9:00, which is impossible, then the probability is also 0. So you see, this is like measuring from 9:00 to 9:00, just a point, even smaller. So I hope now you understand why the probability that the professor arrives in a class exactly at a particular instant of time is 0. So now I'll move on to one more conceptual understanding, that is, you can think about continuous random variables and their probabilities like a mass. The probability of a continuous random variable can be imagined as a density. Sorry, not mass. The mass is for discrete random variables. In terms of density, the probability of continuous random variables can be imagined in terms of density. If you recall, in the discrete case, we started off with the concept of probability distribution, which is a generic name of probability mass function. So for discrete random variables, let me give you a little memory aid. So for discrete random variables, if you recall, for probability distribution, we used the concept of PMF, probability mass function, and we used to represent it with certain notation, say P sub x of x. And then from PMF, we developed the concept of cumulative distribution function. This is already known to you, but when we will discuss continuous random variables, the PMF will be changed into PDF, probability density function. I'll clearly describe what and clarify what we mean by probability density function, but at the moment just remember that this PDF is a counterpart of PMF but in continuous domain. So the probability distribution of discrete random variables is described through probability mass function, and the probability distribution of continuous random variables is described through probability density function. And then the CDF conceptually stays the same, except that the random variables are now continuous. But the path that we followed in discrete random variables was as such. Initially we developed PMF, and then from there on we developed the concept of CDF. But here we'll first develop the concept of CDF of a continuous random variable, and from there we'll see how we can obtain the PDF, or the probability distribution function, probability density function, of a continuous random variable. So now our topic is CDF, cumulative distribution function. The CDF. Remember, the concept is the same. It is the probabilities are cumulatively added up, cumulatively distributed, which means that you take the probability of an interval. Always remember, we'll talk in terms of intervals now, because we cannot imagine the probability of a particular point in a continuous random variable. We'll always think in terms of intervals only, and so the intervals, can be described by integrals in continuous phenomena, and so we'll utilize the concept of integrals and intervals. So cumulative distribution function, the concept of this CDF is roughly the same. You keep on adding up the probabilities of the previous intervals to the next meaningful interval. But now the random variable is a continuous one. So first let me quickly rewrite what we did in case of discrete random variable x for certain values and the corresponding CDF. So if you recall, the CDF of a discrete random variable was kind of staircase until you reach the probability value 1. So you had certain values of random variable x, and then you had the probabilities of those random variable of those values, and then you just used to add up the probability of the next value into the sum of all the previous values, and you obtained the CDF of a discrete random variable x. But when we have a continuous random variable, the CDF notation, remember, stays the same. This is the probability axis, this is the value axis, but since the value of a particular point, so since the probability of a particular value is 0, as our with reference to our previous understanding, so we'll talk in terms of the intervals between the values of a random variable. So now the plot of CDF will obviously start somewhere at 0, and then it will keep on rising because these are the probabilities of intervals that are being added up to the previous values, so to the previous probabilities. So the plot will always rise until it reaches the value 1, and when it reaches a value 1, it shall stay 1 till infinity. So this is exactly the same concept as we did in our discussion about CDF of discrete random variables. So now if this is understood, I can write a few mathematical expressions, and those should be easily understandable. You see here, the probability starts from 0 somewhere on x-axis, and below that till infinity it is 0, and then you keep on adding the probabilities of some meaningful intervals of the values of x to the previous probability. So the plot starts rising. The probabilities are always positive, so there can be no such thing as a negative dip in the plot. It will always rise, and ultimately it will reach the height 1. This height is nothing but probability. So it will reach the probability 1, which means you have added up all the possibilities, the probabilities of all the possibilities of the random variable x. And since beyond that there is no meaningful interval with a non-zero probability, so till infinity you will be simply adding up 0, so it will stay as 1. So now this is a kind of description of CDF of a continuous random variable. I hope this is now understandable. So I'll move on to write the 3 important points with respect to this continuous distribution. So this is given as a theorem in your textbook, and that says for any random variable x, first the CDF of x at minus infinity should be equal to what? Just think about it. The plot starts from 0 at some point on x, and beyond that on the negative axis till minus infinity, it obviously has to be 0. B, f sub x at infinity should always be equal to 1, because you see you have reached a value 1 at some point on x, and beyond that you go till infinity. There is no meaningful interval with probability greater than 0, so you just keep on adding zeros, which does not add up to this total probability 1. So if this is understood, we can move on to this third part that is also easy, and it is also that has also been described when I was giving you some lectures on discrete random variables and their CDF. The probability of an interval probability that x assumes a value greater than x1 and less than or equal to x2. And you know this is nothing but the CDF at the higher point minus the CDF at the lower point. So in an interval you can utilize this expression, but this you'll see later on that this is a really helpful part of the theorem. If you have a continuous distribution, you simply have its expression, you plug in the values of x2 in the expression of CDF, and then you plug in the value of x1 into the expression of CDF of x, and you subtract in this fashion, and you will get the probability of this meaningful interval. Let me give you an example. And see how we can find the probabilities, the meaningful probabilities. So my example is something like this. If x is a continuous random variable, with CDF as this, f sub x of x, and that is equal to 0. For x less than 0, it is equal to x. For x greater than or equal to 0 and less than or equal to 1, and it is equal to 1 for x greater than 1. So you see it's a linear graph. The CDF can be easily plotted as such. This is x, this is the probability axis of the CDF, and you see the plot starts from minus infinity and it shall stay 0 till it reaches a value of x0, and then it shall take a rise in this fashion, which means f of x, which is y-axis now, so y is equal to x, which means a plot with a slope, straight line with a slope of 45 degrees till it reaches a value 1. So you see whatever is the value of x is the value of the CDF. So, and then it from here on it shall stay as 1. So now this is the plot of the CDF. We need to calculate these 4 probabilities. Probability that x is less than or equal to -1 first. B, probability that x is less than or equal to 0.5. C, the probability that x is less than 0.5. D, the probability that x is greater than 0.2. And E, the probability that x is greater than 0.2 but less than or equal to 0.5. So let me solve this now. A part, which means we want to find the probability that x is less than or equal to -1. We have -1 somewhere here, but you see the plot starts rising from the value of x0 onwards. So the probability, and this is the probability axis, so the probability is 0 even in this range. So below -1 obviously it is also 0. So the probability that x is less than or equal to -1 is simply 0. And so we can write that this probability is 0. Part B, what is the probability that x is less than or equal to 0.5? The probability that x is less than or equal to 0.5 can be very easily obtained from here. Whatever the value of x is, the same value for f of x, which is the CDF, because it's a linear graph at a slope of 45 degrees. So if x is, say, 0.5, f sub x is also 0.5. So the probability that x is less than or equal to 0.5 means the total probability. Remember, this is the cumulative probability. So the total probability till x is equal to 0.5 is rising like this, so it is 0.5. The total probability till x is equal to 0.5 is 0.5. So we write this probability as 0.5. Now an interesting note in point C. What is the probability that x is less than 0.45? Please note the difference between these two here. This is loose inequality, this is strict inequality. What do you feel? What should be the probability of x less than 0.5? Is there any difference? I hope you understand that there is no difference. Why? Because we have already discussed that the probability of a point is for a continuous random variable is always equal to 0. So just imagine you take probability till 0.5, x is equal to 0.5, just a little below that, the total is the same because of the continuous nature of the random variable. So we'll also write this as 0.5. So here now we have a new point in mind, and that is strict and loose inequalities in case of continuous random variables behave the same way. So you write for any case probability that x is less than a and the probability that x is less than or equal to a, these are exactly the same. And similarly, the probability that say x is greater than b is perfectly equal to the probability that x is greater than or equal to b. So now, from now on, this point should be kept in mind. So whether we write the inequality as this or the inequality as this does not affect the probability because of the continuous nature of the random variable. And secondly, we know that probability under a point in the distribution of a continuous random variable is always equal to 0. So you see here is this equality means this 0.5 is also included. Here this inequality simply means not 0.5 but just a little below than 0.5. So, and since the probability of 0.5 equal to 0, so you add up 0.5 plus 0, so it stays at 0.5. So that is why these both of these probabilities are the same. Now, D part, and that is we need to find the probability that x is greater than 0.2. What is this probability? We can always write this as 1 minus the probability that x is less than or equal to 0.2. If you remember, if you recall, this is some theorem. Probability of A is equal to 1 minus probability of A complement that we learned in the first chapter. So this can be written as such. This is probability of A is equal to 1 minus probability of A complement. The probability that x is greater than 0.2 is one event, and the probability and x less than or equal to 0.2 is another event which is complement of this. And so we can write these in this relation. So that is why I have written it as such. So now this is 1 minus f sub x at 0.2, because this is nothing but by definition the probability, is the CDF of x at 0.2. You see, probability that x is less than or equal to x was named as CDF of x. So the probability that x is less than or equal to 0.2 is nothing but the CDF at 0.2, which means the total probability till the value of x equal to 0.2. So that is why we have written this part as such. And now you know that f sub x at 0.2 is simply 0.2 because of this plot. If x is equal to 0.2, so is the case with f sub x. So we can write it as 1 minus 0.2, and this probability becomes 0.8. The last but not the least is E part, where we need to find the probability that x is greater than 0.2 and less than or equal to 0.5. If you recall this part of the theorem, it says that the probability of a continuous random variable x greater than this, less than this, can be obtained by writing the corresponding CDF in this fashion. The CDF at the higher point minus the CDF at the lower point. So now we can write it as the CDF at higher point, which is 0.5, minus the CDF at lower point, which is 0.2, and you know that CDF at 0.5 is 0.5 minus CDF at 0.2, which is 0.2. So the probability of this interval becomes 0.3. We'll later on see that we can find the probabilities of these intervals using integrals as well, but I'll discuss this in the next lecture, inshallah. So now I'll quickly review the points that I discussed in today's lecture. Dear students, we started off with the basic understanding, basic concept of continuous random variables, and I gave you 4 important points to remember. Probability of a particular point in the distribution of a continuous random variable, in the probability distribution of a continuous random variable, is always equal to 0. I elaborated on this concept later on. The second important one that I have not discussed in this lecture deeply, but we will discuss it very soon, inshallah, in the coming lectures, that when talking about the expectations and variances, the summation signs that we use in the discrete case will simply convert to integration signs, and the PMF will turn to PDF. What is PDF? Probability density function. So the mass in discrete case The counterpart in continuous case is the density, which is a continuous phenomena. But how we can write it and how we can find this density, I'll discuss in the next lectures. The CDF concept stays the same, except that the plot of CDF of a discrete random variable is a staircase one, and the plot of CDF of a continuous random variable is a continuously rising function until it reaches a value 1. I gave you a quick example of a professor always arriving in a class in a 10 minutes interval. So the probability that the professor arrives, if A is the event that the professor arrives in 10 in an interval, 10-minute interval, then this probability is equal to 1. If you reduce the interval to 1/2, the probability reduces to 1/2. 1/4, the probability reduces to 1/4. 1/10 of the total interval, probability that the professor arrives in the first minute is simply 1/10. So if you keep on reducing the probability, decreasing the probability and reducing the interval, the probability that the professor exactly arrives from 9:00 till 9:00, the probability is simply 0. And that is why we wrote that the probability of a point in the distribution of a continuous random variable is 0. Then I told you that when we were discussing discrete random variables, we first developed the concept of PMF, the probability distribution of a discrete random variable, and from there on we developed the concept of CDF. But for continuous case, we will first develop the concept of CDF, and from there we'll try to derive the concept of probability density function. So the topic that we have discussed is now the CDF, cumulative distribution function, the CDF of a continuous random variable. For a discrete random variable, the CDF is a staircase. For continuous random variable, the CDF is a rising function. Ultimately, it reaches 1, the value 1. Remember, this is the probability axis. The probabilities are being cumulatively added up in terms of the probabilities of intervals. Then we discuss the theorem, important theorem. The CDF at -infinity is always 0, because coming from -infinity onwards to the positive axis, you come across some interval with non-zero probability, and below that it is obviously 0. So you simply add up this probability to 0. So the graph rises a little. Then you reach another interval, for example, this with some non-zero probability. So you add up the probability, so the graph rises again, and so on. Ultimately, it reaches 1. And since now the meaningful intervals have been completed, no further meaningful interval there, so the probability shall stay as 1. The difference between the two is this is a staircase for discrete random variable, and this is a continuously rising plot. That is why f sub x at -infinity is equal to 0, and obviously f sub x at infinity is equal to 1, because you reach 1 and then you simply add up probability 0. So adding up zeros to 1 will always give you 1. So the plot shall stay at 1. And this was also an important part of the theorem. The probability of an interval on a continuous random variable can be found as such. Write the CDF at the higher point minus the CDF at the lower point, and then do the subtraction, and you will find the probability of this interval. We augmented the understanding of this theorem through an example. We took a very simple example of the CDF in this fashion, and this is plotted as such, and we need to find these 5 probabilities. Probability that x is less than or equal to -1 is simply 0. Why? Because the first meaningful interval is found at 0 onwards, not below. So beyond -1 it is obviously 0. What is the probability that x is less than or equal to 0.5? It is 0.5 because this is a plot at 45 degrees. Then we also discussed that this inequality and this inequality behave the same when it comes to continuous random variables, and that is why you have the same probabilities for both of these cases. So always remember, when x is a continuous random variable, this probability and this probability are the same, and similarly for the greater than and greater than or equal to signs. For D, what is probability that x is greater than 0.2? We can easily write it as 1 minus probability that x is less than or equal to 0.2, and this has been derived from this basic theorem. Probability of an event is equal to 1 minus the probability of the complement of that event. So now this is nothing but the CDF, because the CDF is written as such. Always the probability that x is less than or equal to x, this expression is nothing but the CDF. So this part has been written as the CDF, so it is 1 minus the CDF at 0.2, which is 0.2. The total probability, so the resultant probability for this case is simply now 0.8, and this last one is this is what I just discussed in terms of this C part of the theorem. Probability of an interval of a continuous random variable can be found by utilizing probability, the CDF at the higher point minus the CDF at the lower point. So this is what we did exactly, and we have found that this probability is 0.3. So this was lecture number 2 of week number 11. Dear student, thank you very much for your time. I hope you are frequently visiting and trying to understand the concept, and you are frequently visiting your textbook as well, trying to solve a few end chapter problems as well. Xavier will give you assignments on some regular intervals, and then will give you time to complete those assignments and send the solutions back to him for proper assessment. Thank you very much.